this sheet of paper.
Yo,
So this is going to be like your most important thing that you're going to have to go through.
My soul.
So we're going to start with kind of the classic one, all right? So if you look at that diagram, what? So let's start with this idea. Because you have to have this straight. That's the lens. Is it concave or convex? Convex. Okay? So over here, you've got a pencil. Could be a candle, could be whatever it is. But you always want to use something that has like a noticeable top and bottom. Okay? Don't do a stick, don't do a circle, you can't tell what happened. Now, in reality, we usually do what's known as the principal rays, okay? Which are these three. So what the yellow dots are representing is what we call the focal length, okay? Focal lengths are fixed values based upon the structure of either the mirror or the lens. You can't change the focal length as long as you are in air. Okay, now you take the lens and you submerge it in water or a different medium, then you can change the focal length. But as long as you're in air, which you're going to be, unless I specifically tell you differently, you assume that it's in air. So these three are what's called the principal focal or the principal rays. So how you draw these, and this is all about the sequence. Notice that there's three of them. The first one, see that center dotted line? Okay, yeah. That's called the principal optical axis. Okay, that goes through the middle. Boom, there you go. At right angles, that's at right angles to the center line of the lens or right angles to the center line of the mirror. Then everything is based upon that. So this is as simple as it gets in terms of the diagram. So you take the end of the pencil, draw a line, boom, parallel to that primary optical axis. It hits the lens. The whole point of the lens is to make the light bend. Okay? That's the whole point of this, make the light bend. So the first one, you go parallel, it hits that lens, and then it's going to go through this focal point, and then it's going to end up over here. Now, this is, at the beginning, it's like a mystery, and you're trying to figure out where the image could possibly appear. So, on the first one, if you were actually doing this, this actually shows all three at once. But in reality, when you draw these, you're going to draw them one at a time. You can't, just draw all three at the same time. No, you can only draw one at a time. So if you were to draw that first one, it would hit here. You know it would come through this focal point on the other side. And then it's just going to go at some point over here. So the first ray diagram, this first one, all that does is that it shows you that it's going to be somewhere into that region off to the right. Okay? If that's all you had was that first primary ray, you would know it's just somewhere over there. Now, you could also figure out, since that's the tip of the pencil and that light gets inverted and flipped over, that image is going to be upside down because it's going to go through that focal point and down. So odds are it's probably going to be an inverted image. The second one starts at that same point, and it goes right through the middle of the lens, right at that intersection of that optical axis and the center line of the lens. Boom, straight through like that. Now, what that would tell you, if you didn't know where that third line was, if you were actually drawing these, you go, okay, right, hey, here's my second line. It would intersect with that. So what that's telling you is that, now I know where the image is going to be because that second line intersected there. What the third line does, the third line is just a verification that says, hey, is this really what's happening? So the third line goes through the focal point on this side, hits the lens, gets refracted, and then goes parallel with it. So what the third line does is that it basically says, hey, let's verify that the other two lines are right because it's going to intersect at that same point. So that's just like a check to make sure the first two are right. Now, we draw these as these three primary rates. In reality, if you were to do this of many, okay, so in reality, what's happening is that photons are bouncing off of the tip of that pencil. Only a small number of them are actually going through those on those three primary rays. They're spreading out all over. But what that's showing you, even if you look at those three, if you were to draw a whole bunch of them that went through that lens, they're still going to end up here. Now, this is showing just the ones that get to the tip. Obviously, you're seeing the entire pencil. If we do it just for the tip of the pencil, then in reality, you're generating an image of the entire pencil. Okay? So don't look at this and go, oh, you're just going to see the lead or the writing portion of the pencil. That's not what you're doing. You're going to see the whole thing. But what this tells you is where the end of the pencil is. And then you can go from there. Okay? Cool with that. Now, if you look on that sheet that I gave you, now we're going to make the math work out. So I want to go back to the principal rates. So on this one, the other thing that you have to decide early on when you start to do these problems is what's the sign of the focal length. Because you're going to have three different distances: your image distance, your object distance, and your focal length. Your focal length, like I said, you can't change that based upon the structure of the lens or the mirror. But what you can do is you have to decide if the focal length is going to be positive or negative. Okay? So how can you tell if the focal length is going to be a positive or negative number? We talked about this yesterday. No?
It's like convex.
What do positive people
they
do?
bring people together.
Positive people bring people together. Negative people make things go away. So, what's this lens doing?
Bring people together.
Bringing them together, right? Because of the fact that it is a convex lens. Convex lenses bring people together. So convex lenses are always going to have a positive focal length. Okay? Cool with that. Always positive. No exceptions. Always positive. This light's always going to be brought together. Okay. Now, so we're going to do some math. Okay? So on the one that I gave you, so we're going to start up here with this one where oddly enough it has like an arrow here and it's got the convex lens. So here's what you've got. This is what I gave you. You got this, that's that primary optical axis. Okay? And I drew an arrow. You could do a candle. You could do a bicycle, a carrot. I don't care. Pick one. Okay? It's up to you. So, what I've given you is the fact that the object distance is 40 centimeters away. Now, that's your SO. The beauty of your object distance is that you don't have to guess the sign of the object distance. Object distances are always positive. Okay? You don't have to guess on that. There's nothing to think about object distances. Object distances are always positive numbers. Okay? Nothing to think about. It's always positive. Now, I also told you that the focal length here is 20 centimeters. So when you're drawing these diagrams, and you're going to draw a lot of them, okay? There are certain things that you always label. Three things on any ray diagram you always label: the focal length, the object distance, and the image distance. Okay? Those are the three that you always, no matter what, mirror, lens, inverted, virtual, upside down, right side up, Monday, Friday, doesn't matter. Those are the three that you always label: your focal length, your object distance, and the image distance. So, now, in this one I told you that the object distance is 40 centimeters. Boom. My focal length is going to be 20 centimeters. We have that number. And that's going to be a positive number because the light's going to be brought together. Okay? Now, typically, 95% of thin lens problems, you're trying to find the image distance. Okay, that's what you're searching for most of the time. So in this situation, you've got 1 over so plus 1 over psi equals 1 over f. So get in touch with your inner inverse button on your calculator, okay? You're going to be using that number a lot, okay? You're going to be using the inverse function key a lot because these are all inverse functions. So here's what I've got. I've got an object distance of 40 centimeters, so I know that number. I know my focal length is 20 centimeters, but that's going to be positive because the lights are being brought together. So what I'm searching for is the image distance. What?
Since it's 1 over so, 1 over psi, and then 1 over f, can't you just do so plus psi equals f? Or?
No, because of inverses. No. You have to take the inverses and then do the mathematical operation. Okay? So, in this situation, there's a mathematical way that you can find this, and then there's using the ray diagram to find it. So this is the mathematical one. So, in this situation, I've got a positive focal length. If that light had been spreading out, my focal length would have been a negative value. So here's what I've got. So I've got 1 over 20 minus 1 over 40 equals 1 over psi. So to get psi, I'm going to subtract it first and then take the inverse of that. Okay? So what do you get for your image distance? 40? Okay? 40? Cool. So what that tells me is that the image, if I draw these ray diagrams, which is tough to do freehand, but I'm going to try. Okay? So I got that one. I got that one going straight through. This is a good horrible. That one goes through that focal point. Okay? So that tells me where that's going to be. So right away, what do you know about that image? Is it upright or is it inverted? It's an inverted image. Okay? Now, this is what I showed you yesterday. I can project that onto a screen. Okay? So because I can project it onto a screen, what does that make it?
Real image.
Real image. Okay? So this is a real image that's inverted. So, fun fact, this is how your eyeball works. Okay? Your eyeball is a convex lens. So here's the odd thing about us human beings and our eyes. You are actually seeing me upside down. Okay? The image that's formed by your retina is upside down. Okay? Everything you've ever seen in your entire life is upside down. But your brain flips it over. Okay? Kind of a cool adaptive thing. But the actual image that's on the back of your eye is upside down.
And it does it that fast? I think I've been knowing that.
Your brain just gets it and then flips it.
Yeah, I've been knowing that.
Because it's simple. It's just this is how your eyeball works.
Is there any brain thing
No, you're joking.
Dude, this is
like,
day one
it doesn't like turn around?
If it does, I've never heard
You
of it.
didn't wait, Big Mike. That's the question I asked you.
Yeah, if there is, I've never heard of it.
Yeah.
Okay? So that was kind of a cool adaptive tool that somebody came up with. Yeah, let's put that over.
You should have been on YouTube.
Okay.
And you're like,
Now, when you get to magnification, so there's a couple of different ways that you can do magnification. Okay? So if you look at what's on your equation sheet, let me get that.
Oh my god, it's a thing.
So your textbook, and I don't know why, gives an absolute value of either pi over ho or psi over so. Okay? P phi pho pho. So what do you think HI and HO are representing?
How did the image and how did it?
Image height? Okay. Image height. That's your image, and this is your object. And this is your image distance. And that's your object. Now, practically, let me give you a hint. So how typically, and like I said, your book does this weird absolute value thing. It's also handy to put like a negative sign in front of that, and I'll show you why that works. Okay? So typically how this plays out, you're typically after your psi and your so. Because you're going to know distances and you're going to know focal length and you're going to have things like that. So I'll show you the importance of that negative sign in just a second. So your book lists this as an absolute value. About every other textbook and optics chapter in the world puts a negative sign in front of it. Okay? They put absolute values. I don't know why, but they do. Okay? Because a lot of times if you know the sign of your magnification, that will tell you something important, which you'll see in just a second. So in this situation, my psi was, I'm going to put that negative sign in there. So that's negative 20 centimeters over 20 centimeters. So I get a magnification of
-1.
-1. So what that tells me is that if this was like 2 centimeters tall, okay, like you had a 2 centimeter tall image, you would make that image be 2 centimeters. So if your object was 2 centimeters,
Devin.
that would be 2 centimeters.
What?
But notice that
Stop.
that now there's a -1 in front of this. Okay? So notice that negative sign, and I also have an inverted image. Okay? So if you come up with a negative magnification, what you'll see is a trend. The negative magnifications indicate that the image is going to be inverted. Okay? So that's the significance of that negative sign. So here's what's important. There's 2 ways you can do magnification. Pi over ho, psi over so. Okay? Your equation sheet doesn't put the negative sign on there. Okay? Your textbook does, which is weird. Okay? That's why I don't like the AP sheet. But I always put that negative sign in front of it. Okay. So, magnification, -1. Is it upright?
No.
No. Is it real or virtual? It's real. Okay, now, I'm going to talk about what's going to happen to the magnification if so is increased. Okay? So, Ben Shannon, why this?
Because it's in the denominator, so they're inverse.
Okay?
So in magnification inverse.
So, can I change the focal length?
No.
That's a fixed value, okay? Because that's a property of the lens. So if I made my object distance bigger, let's say I push that up to 60, okay? So out of curiosity, somebody do the math. Take 1 over 20 minus 1 over 60, and then take the inverse of that. 30. Okay? So my image distance is now 30, which is also, right? So I went from an object distance to 40 to 60, my image distance to 60. Now, if you look at this in terms of magnification, okay? So my psi is 30, but my image was, so my magnification becomes -0.5. So my magnification is now less than 1. So it's going to be half the size. Yes, Olivia Pruitt.
Okay, I'm confused. Where did the 20 and the 30 come from? Because I thought it was 40. I'm lost.
It is.
We're doing an example.
No, I just changed the numbers. I said if we change the object distance to 60.
Okay. I got it. Okay.
Yeah, so we're just changing it to a different set of conditions.
Okay.
Good with that.
Yes, sorry.
Okay, no, we're good. We're good. Now, I can also do this by just moving this, okay? Notice that I moved that further away. What happened?
Small.
Get smaller. Okay? I bring it closer. Bigger.
Oh my gosh.
Whoa!
Whoa, time out.
Whoa!
Wait.
That got weird.
Again, I wasn't
Oh! Oh, no,
That's not possible.
Whoa!
That's not possible.
Whoa!
Stop, stop. Time out. Time out.
Okay, wait.
Fake news.
Hold on.
This is not real.
Make it sound like I need to do an exorcism. Okay. Like that better? Here, we move that.
It's not moving.
Oh my God.
Yay.
Then we did this.
Stop.
Okay. Now, there's something important though. Something important. Hey, whoa. Stop. Stop.
Is this black
Okay.
hole stuff?
Is this what?
If you go in a black hole, you go into the third
No,
person.
okay. So there's a couple of things that are important about
Am I the only person here with 13 hours of sleep?
Yes.
There are a couple of things that are important. This is still the object, okay? But notice that I've moved it inside the focal length, okay? So that's important, number one. The focal length is still the same, okay? It's still the same focal length, but I'm inside the focal length. So that's the first thing to observe. Also notice that now you still have these lines going like this, but now this program is showing them as dashed lines. And this is true of optic diagram. So what's happening is that these lines are still going this way. But what's happening is that part of that light is getting refracted back. So when some of that light gets refracted back from the lens, that's what we show as dashed lines. So what's happening is, imagine if you had your eyeball out here, okay? Your eyeball, and this is the kind of leap of faith that you have to take. You're seeing this light going out like this, but if your eyeball is here, your eyeball tries to recreate that path that it came from. So your eyeball would try and say, oh, it actually is here, because that's what you're seeing, because your eyeball sees these lines coming back, and that's why you have those dashed lines. Now, let's do the math. Okay, show up. Let's do the math. Okay, so this is the second diagram over here. Okay, it will just show up. So on that second one, so here's what you've got. I've still got that same lens. Okay, still got that going. I still have the focal length out here at 40. Okay, so I made the focal length 40 just because it made it a little bit easier to draw.
Okay.
Okay, and I've got the object here at 20 centimeters. Now, is my focal length still going to be a positive value? Yes, because of the fact that when it hits this, it's still trying to converge it, okay? So that's still a positive value. So my focal length is still positive. My object distance is always positive. You don't have to think about that. I'm trying to find the image distance. So here's the importance of this. So you know that 1 over psi, you always start with this, plus 1 over so equals 1 over my focal length. What are you trying to find?
Image length. Size.
You're trying to find psi. So 1 over psi is going to equal 1 over f minus 1 over, and then so my psi is going to be the inverse of that. So somebody take 1 over 40 minus 1 over 20, and then take the inverse of that. What do you get?
Negative 40?
I get negative 40. I get negative 40. Okay? So, now, just back up the bus. Just a second. We need to be able to start to recognize trends. Okay? So, when I do the magnification, and we said magnification was negative psi over so. True? Okay? True? So I've got a negative of a negative
So it's not inverted.
divided by my so, which was whoa.
It's upright.
So what do you get?
2.
Positive 2
No way.
for your magnification.
Yo.
So now notice that this magnification is positive. Why? What does that indicate?
It's upright.
It's upright,
Right.
but it's big. Okay? Big. So if you go to this diagram, okay, this is what this is showing. So I've got this right here. Okay, here's my object.
See.
There's my image. Notice that that's big, right? It's big. It's upright. It's the math, right? Virtual or real? Virtual. Now here's the reason why it's virtual. Okay? Here's the reason why it's virtual. The light itself is going in this direction. Okay? That's the path of light. Part of that's being reflected back. That's what you're seeing. Now, in reality, this is exceptionally difficult to actually do and see. You can make the math work, but to be able to actually do this is tough, mainly because of the fact that you have this virtual image back over here. That's on the other side of the object. You can make the math work, and you can do it, but it's exceptionally tough to pull off. This one, I promise you, optics honor, okay? I'm not going to have you do anything like this, like on the lab or the test, okay? But I do this just so you can see the trend, okay? Now, here's another thing I want you to get out of your minds right now. And you're going to think, oh, the image always forms at the focal length. No, it doesn't. This one just happened to, okay? So get out of your minds that the image is at the focal point. And it's not, okay? Your image is going to be whatever satisfies that thin lens equation, okay? So get out of your minds right now that the image appears at the focal point. It could, but it's not, certainly not an absolute truth. Thanks, Jen.
So all like magnifying glasses and scopes, they produce virtual images.
Oh, no. We'll get into that.
Huh?
Because microscopes, those are compound lenses, and that math gets weird. This is just a single lens. Yeah. Well, no, magnifying lens itself is just a single lens. He was talking about like microscopes.
Will we ever get advice?
Huh?
Wait, is that quantum scissors like at the end?
Yeah.
Wait, so you
Okay.
Wait, what's that?
So here's what I want you to see. If I take this and move it back, okay? And again, here's what I want you to see. This is, when you have a convex lens, this is how this is going to play out most of the time. You're going to have an image over here, and this is like the perfect example of this idea that the image does not form at the focal length, okay? So get that out of your mind. So if I move this, and I change that, I can change the magnifications. I can't change the focal lengths because those are set in stone. Okay? Got that one. I show you this. It's more theoretical. In practicality, we're never going to do that in the lab. In terms of where you have it inside the focal length. Okay? Outside, that's bread and butter right there. I promise you, that's bread and butter. Okay, that's like butter. You're on a roll, baby. That's gonna happen. Okay,
Peanut butter and sardines.
only if
Peanut butter and sardines.
Okay, so got that one. We're good. Okay, good. Now we're gonna change it up. Oh.
Hey, concave.
Does this make it better if you do this?
Yeah.
Like, is it more
It
emphatic?
like locks you in.
Negative focal length, right?
Okay, now hold on, just time out. What?
Before you move on, what's like the AKA at the top of the paper?
Okay, so a converging lens is the same thing as a convex lens. Okay? But then the next one down, a diverging lens is a concave lens. Their terms are used interchangeably. Okay? Now, let's talk about this one. Olivia Pruitt, convex lens or concave lens? This is easy. Shush! I specifically said Olivia Pruitt. You do not look anything like Olivia. Okay? Yeah, shush. Olivia Pruitt, concave or convex?
How are you asking me?
Because you were all about, oh, this is how I remember it, so here's your chance.
Oh, wait. Which one? This one? Oh, concave.
Why?
It makes it see.
Look, you go into the
Yeah,
cave.
see, Shannon gets it.
Yeah, but if it's over here, that's not a C.
That's basically a C.
It's a backward C.
Okay, but then if it's convex, it's also making a C.
It looks
Oh,
like
just
okay.
on this side.
I like the cave analogy better.
And
I'm
it
walking
goes start with the
into
C.
cave. Okay?
Yes.
That's my story. Okay, cool, fine. All right. Now, this one is also tough to do. But this is the one that I showed you yesterday where you had like that floating four. Okay? That's what happened with this one. Okay? Stop! It's annoying. Okay? I don't need to have my statements of fact reinforced by my fellow students going, God! Okay. Like what my blood pressure is doing right now? That's what's happening. My heart rate. Okay.
Only two.
Up as well.
Oh.
Not TOO. Okay. So this one, promise you is going to be there. So here's the story.
Let me leave.
Since what's happening with the light?
It's
being
shot out.
And
Once it's going
so
out,
my
it's
focal
negative.
length is going to be
Negative,
a
negative.
value. Okay? So here's the story. So let me kind of go back and we'll do the math on this one.
What's the horizontal
Looks like a face.
Primary optical axis.
Primary optical axis. And the
On the left.
vertical
I don't know.
That's just the lens.
Optics is making me see things. It's almost like that's what it's supposed to do. It's so funny.
Yo, Mr. Perkins using AI?
No, I'm not.
He swore against it.
Well, you round
It is not 120.
You round that up to 130. You round that up to 2.
It is not 120.
Okay,
It's 127.
so this one gets a little bit wonky, mainly because of the fact that you're creating an image that's on the other side. So let's talk about right from the beginning. Do you think this is a real or virtual image? Virtual. It's going to be a virtual image. Now, here's why, like if you try and look on the other side of this, as that light hits, okay, you run that parallel with it, okay, that's going to diverge and go up like that. Okay, so all of these images, when they hit, are going to go out like this. Now, in terms of this focal length, okay, so what's going to happen is that this, you draw this one coming in like this, is going to hit this, is going to spread out. So there's a couple of ones that you can always draw. One